Alright guys, so in this video we are going to be building functions from functions with composition. And what that means is we're going to be taking one function as the input of another function. So basically what we want to do right here is break down what the functions are actually doing to their inputs, and then we can think about what that means to put a function inside another function. So right here, if we're looking at f of x, we've got x squared plus 4, but just f is the operation that we're doing to x. So that means f is going to be squaring the input and then adding 4 to it. If we're looking at k of x, that's 1 over 2x, but just k, the operation, is taking an input, multiplying it by 2, and then dividing 1 by that number. Right here, when we look at g of x, we've got the square root of x plus 1, but g as a series of operations is basically going to take an input, add 1 to it, and then take the square root of that number, right? So when we talk about composing functions, we're basically going to be plugging a function into another function. If we're looking at f of g of x, this little circle is of, we would say that that would be g of x inside f of x. So this is f of g of x, right? And now right here, when we're thinking about what this function is going to be, we basically want to think that f itself is squaring something and then adding 4 to it. And plugging in our g of x is basically going to be plugging in that equation. So that's squaring the square root of x plus 1. Now, when we're evaluating the domain of these composition of functions, we want to evaluate the domain at the instant that we put the two functions together. And what we're going to do is first look at the domain restrictions for the inside function, and then think about the domain restrictions that we're going to get for the composition of the functions, right? So what are the operations of the outside function going to do to that domain? So right here, we can say that immediately we cannot have x be less than -1, right? And we're not seeing any additional restrictions come from the operations of f onto g. So right here, we can say our domain is going to be from and including -1 and positive infinity. Now right here, after we simplify, we can see that the square and the square root are going to cancel out, which gives us x plus 1 plus 4. And that means that the composition f of g of x is actually going to be x plus 5, the graph of x plus 5. But again, that's going to be on the domain from -1 to positive infinity. So a lot like the other functions we've seen, we're going to see a graph that basically is the linear function x plus 5 on the domain from -1 to positive infinity. So let's start at the ordered pair. That would be, let's see, about right there. And now we're talking about a slope of 1 and the y-intercept of plus 5. So it looks something like that if you typed it into the calculator. All right. So what I want you guys to do is to try these next two problems. Now, these are more challenging problems. So it's worth it to take a second and really think about what you're looking at after you combine the two functions with composition. And then we'll come back and look at these together in a second. So right here, we'll pause the video and let you guys try these two compositions of functions on your own. All right, guys, let's take a look at these two compositions. So our first composition is g of f of x, so that's f of x inside g. Remember that g is the square root of an input plus 1, and f of x is x squared plus 4. So right here, we've got our equation for f of x inside g. And if we take a look at this composition, there's no restrictions for x squared plus 4. Now, we would normally say that what's underneath the radical, that square root, that even radical, cannot be less than 0. But if we take a look at this, we've got x squared plus 4 plus 1, and we're saying that can't be less than 0. If we sort of simplify this expression, we can see this as x squared plus 5, that cannot be less than 0, And thinking about this, every x value we plug in is immediately going to be squared. So all the negative x values that we would plug in are in the end going to be positive. And then we're adding 5 to them. So there's no way for this expression to equal 0, let alone be less than 0. So actually composing these two functions gives us a domain of negative infinity to positive infinity. And the simplification we would do here is basically just what we did right here, which is taking down our parentheses and combining like terms underneath that square root. So our g of f of x is the square root of x plus 1 plus 5. All right, so next we're going to take a look at k of x, another interesting one. And right here, basically what we're saying is that we're putting the function k of x inside k. So remember that k of x, can't see it here, but it's at the top of the page, you guys can see it, is our 1 over 2x, right? And basically what we're saying is that we're plugging that inside k. So k is going to take its input, multiply it by 2, and then divide 1 by that number. And basically we're just plugging in k of x, that equation, into that input, right? So right here, immediately when we're looking at this expression, we're going to say that for our inside function, we cannot have x equal to 0, right? And then we want to think about what restrictions the composition of the two functions are going to give us. And here we would say that in this composition, we can't have the denominator 2 times 1 over 2x equal to 0, since this expression is in the denominator of the composition. But again, if we take a look at this, maybe even simplify it a little bit, right here we've got 1 over x, and there's no way for 1 over x to equal 0, right? There's no x value we can plug in here that is going to make 1 over x equal to 0. Plugging in 0 would make us undefined, and then that's really sort of anything you might think of, I think. But so right here in general, we can say that the only restriction we have is that x cannot equal 0, and the composition, the entire expression, isn't giving us any restrictions. So that gives us a domain from negative infinity to 0, union with 0 to positive infinity. And right here with our simplification, when we go through this, we can see in the denominator we're multiplying by 2, and we've got a 2 that we're multiplying in the denominator, so that's like a division of 2. Multiplication and division are going to cancel out, and that gives us 1 over x. Now we're dividing by a fraction, so multiplying by the reciprocal of our fraction in the denominator, 1 over x, would give us 1 times x over 1, which is really just x. So right here what we're looking at is k of x as x, the linear function x, where we basically do not have an ordered pair at 0. So it's a bizarre removable discontinuity that we're seeing here. You basically get the identity function with a hole at 0. But that's what this guy is going to look like. All right, guys, so we are going to now talk about evaluating for a given input with these combinations and compositions of functions. And I'm going to talk about, really I'm going to talk about 2 ways of doing this, but I think that there's one way that's specifically easier than the other way. So first off right here, we basically just want to see that we're looking at a specific x value plugged into our composition or our combination of functions. So looking at A, we've got f of g of 2, right, which is f of g of 2, like this, where we're basically applying g to the input 2 and then applying f to the number that we get for that g of 2, right? Now, the 2 ways we can do this is we can first evaluate g of 2 and then take that number and plug it into f, or we can take the composition and then plug 2 into that. So I'm going to do the evaluation of g of 2 first, and then plug that number into f first, and then we'll see that we get the same thing when we first compose f and g and then plug 2. So g of 2 is going to be the square root of 2 plus 1, so that gives us the square root of 3. So we can say now that g of 2 is the square root of 3. And then at this point, we're going to take that square root of 3 at g of 2 as the input for f. So f is going to take our g of 2 which is the square root of 3. So that's f of the square root of 3. And it is going to do what f does, which is square the input and then add 4 to it. So right here, we've got the square of the square root of 3 plus 4, and that's going to be 7. So right here, that's the work that we would do when we first plug it into the first function and then take the output that we get for the x value for our first function and then plug it into our outside function. If we were to compose f and g, f of g of 2, then first we would say that f of g of x would be, and then we did this on the previous page, f of g of x we said was our x plus 5. And right here, plugging in our 2 into this composition, so saying that x is going to equal 2, would give us 2 plus 5, which gives us 7. So we're seeing that we get the same thing either way we choose to do it. I kind of think that it's easier to evaluate the input for the inside function first and then plug that output into the outside function to get the number in the end. If you've already got the composition, that's obviously pretty easy, but you guys can choose how you want to go about that. So let's go ahead and sort of condense this work. I'm going to do that right here. This is going to be a little bit weird. It might get really small. We'll see how it goes. So I'm going to group this together, group it, and then I'm going to shrink all that down. Oh, that's not so bad. That looks all right. And now we'll take a look at k minus g of 3. So right here, basically what we're saying is that we're subtracting g of 3 away from k of 3. That's basically what this combination of functions for 3 is going to be. So right here, again, I think it's easiest just to evaluate these two and then subtract their two function values. So right here, k of 3 is going to be 1 over 2 times 3. And then we're subtracting away g of 3, which is the square root of 3 plus 1. So here we're going to have 1/6 minus, and then the square root of 4. And then this is going to give us 1/6 and then minus 2. Now right here, getting 2 to be a fraction with 6 in the denominator, we would have 1/6 minus, and then this is 12 over 6. And then finally right here we can say that would be negative 11 over 6. So k of 3 minus g of 3 is negative 11/6. Okay, guys, so we're going to have you try these next two problems, and then we'll come back and take a look at these together. All right, guys, so looking at these last two, we've got g of f of negative 5. So that's negative 5 first plugged into f, and then the output of that plugged into g. So first we evaluate f of negative 5. Squaring negative 5 and adding 4 gives us 29. So f of negative 5 is 29. So then we evaluate g of 29, and that is the square root of 29 plus 1, which gives us the square root of 30. It is approximately 5.477. Okay, so we're looking at our next combination for a specific x input. We've got f divided by k of 3, which is f of 3 divided by k of 3. So evaluating f of 3, we've got 3 squared plus 4 gives us 13, and k of 3 is going to be 1 over 2 times 3, so 1/6. Now right here we're dividing by a fraction, so right here that's equal to multiplying by the reciprocal, so that gives us 13 times 6, and that's 78. All right, guys, so hope we're knocking the rust off of this from Algebra 2, and we'll look at more of this stuff tomorrow.